Okay. I'm sorry about the delay. I had some issues with the car. So um, so today, hopefully, I can finish the coin simulation and animation, and about also I'll tell you how you can use your code or your equations from your Mathematica to type it in your Python script so that you can perform the simulation and what aspects you need to consider to do the simulation. Okay, I'm gonna cover that, um, and after that, um, so next time I'll start about the control part. But the control part will be very simple and brief. Especially, I'll try to do something that can be applicable to your simulation. Because if I just simply handle theory only, then maybe it has nothing to do with control of the dynamical system. But I think it will be more interesting to study, to cover that, to cover how to control the real system uh, using control. That will be more interesting and beneficial for you. So I'll try that. But still, it will be very limited because we don't know how to control the nonlinear system yet, right? Okay, in our system, the equations of motion that you derived from whatever any system you have is mostly it's nonlinear system. So it's very hard to control that type of system, but uh, we'll see if I can do it. Well, we need a process called linearization uh, to 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 make the system linear, and then I'll introduce maybe one or two methods to control the system. Okay. Okay. Anyway, so let's look at what we did last time. Um, so yeah, so let's look at this one first. So this is Euler-Lagrange equation for coin, and here I assume there's no friction. Okay, makes sense. And so that means the coin is rolling on the ice, on the ice, right? But there still exists some vertical force, but no horizontal or friction forces. Okay, so that's the situation. And everything else is the same about the kinetics or kinematics. So you have to set up the reference frames. Um, so here, define reference frames and define the coordinate systems, and the direction cosine matrices, they're the same. And you can just move on. You define the center of mass position. In this case is, so this is the center of mass of the coin. Okay. This is the contact point position, and then you're adding R. So in other words, you add this vector plus this vector. Okay, and once we have that, then well, this is the automated version. You can just run kinematics or kinematics. It will give you all these four variables. So it will compute the center of mass velocity, center of mass acceleration, and also angular velocity and angular acceleration for you. But even without using these functions, you know how to calculate the velocities, accelerations, right? Okay, and then the next step is then now we have to do the kinetics part or dynamics. So the first thing is you assign mass or inertia. So let's assume that the mass of the coin is m. So it's m, and then the moment of inertia is defined in this way. Again, this requires 6 elements because the matrix, the moment of inertia matrix itself is 3 by 3 matrix, but it's symmetric, so that's why it requires only 6 numbers. Okay, so this is how we define that 6 numbers, and I already explained this one before. And once you just define inertia, moment of inertia in this way, then now we're good to go. And we have another one is for this automated version, the system doesn't know which direction is the vertical direction. Okay, so we just say that N3 is the vertical direction, which is the opposite direction of the gravity. Okay, once we have that information, then we are almost ready. And the only thing left is then think about the Euler-Lagrange equation. Right-hand side, you have the non-conservative force components, right? So you have to define that. So that needs to be specified. And that one, here we only have tau. So again, tau is, if I go back to here, I apply tau only in this direction. So that means we're applying some torque in this direction. So again, I explained that this is quite similar to you're riding a unicycle and then you're actually pedaling the system so that you're applying the torque at the wheel. It's something like that. But otherwise, we don't have any other external torques or forces. Okay. And remember that this tau or this torque is aligned with this B3 direction, or in other words, it's aligned with Q3, right? So that's why this tau is the third component of the Euler-Lagrange equation. Does that make sense? Okay, but we don't have any other forces. For example, Q1. Q1 is actually related to steering of the system, right? If you have the wheel handle of the system, then you can say that's your steering torque, but we don't consider that one in this case, so we don't have that torque. What about the Q2 part here? We don't also have the torque for Q2. And what about Q4 or Q5? We don't have that forces in here directly. Okay, so that's why we have only the torque about Q3, and that is put in here, only in the third component. Okay. Yeah.
So you don't include your normal force.
Normal force exists, right? But you have to think about whether that normal force is contributing to the virtual work, the work. So remember, at the contact point, so your force is applied at the contact. So here, right? And if you look at the contact itself, that position doesn't change, right? It's always at the surface. Or in other words, the height is always 0, right? So it's not contributing to the work of the system. So that's why we're not including them here. Yeah.
When you said the P doesn't move, are you talking about the B and C reference frames?
So yeah, this P. So again, we can think about so P is the contact point at the contact point, right? But then so contact means it's between two rigid bodies, right? So one is the surface and the other one is the disk, right? So P is on the surface. So that's why that point P is not moving. But then the other side is what? The other side is here, which is on the disk or a coin. That one is moving, right? That may move, right? If it's sliding. So if we say that point is Q when Q3 is 0, right? Then P and Q are just coinciding, right? Yeah. Okay. Okay, so once we define the non-conservative forces here, then we're good to go. So we just completed all the Euler-Lagrange equation components. You simply solve it, so you know the equations of Lagrange equation. Then you simply run this command EL equation, and so you get this expression. Okay. So it will have 5 equations, okay, because you have 5 generalized coordinates. Okay. So if you look at the first one, for example, so this you will see there is a comma here. So here we have comma, right? So that means this is the first equation. Okay. And this one equals 0 because the non-conservative force is 0, right? The third one, yeah, and as you can see here, this is the third one. This is the third equation. Okay. And this one is 0, and as you can see, there is a tau involved. All right. So anyway, so that's our equations of motion, and the next step is then once you have that expression, then now we have to convert this one into q double dots. Okay, that's the reason why we need the q double dots is this. Let me see. So I already explained this one, but here. So we need this expression to do the numerical simulation. Okay, you have seen this expression before, and so we need this form x dot equals f of x. So x dot equals something. We need that expression. So this is first order form, right? So we need to have that expression, especially in our case, our x state variable is defined as q1, q2, q3, q4, q5. This is the configuration variable, and then we also need q1 dot, q2 dot, q3 dot, q4 dot, and q5 dot. And the reason why we're including velocity term is that the mechanical system we're dealing with is second order system. Okay, that's why we are including both position and velocity. And if that's the case, then what is x dot? X dot is now q1 dot, q2 dot, q3 dot, q4 dot, q5 dot, and then q1 double dot, q2 double dot, q3 double dot, q4 double dot, and q5 double dot. So so q1 double dot to q5 double dot, that's already defined. Okay, that's already known because that's the velocity term. The problem is we have to have expression for q1 double dot, q2 double dot, q3 double dot, q4 double dot, and q5 double dot. And these double dots are coming from the dynamics. Okay, so you have to have that expression, and so as you can see, so q1 double dot, q2 double dot, q3 double dot, and where's q4? Q4 double dot here and q5 double dot. You have to enter that expression in your simulation. That is initiated. Okay, so that one has to be entered in your script, Python or MATLAB script, and then you simply run the numerical integration functions. If it is a MATLAB, then you can use OD45. If it is, well, for generic algorithm, you have to use longitudinal method. Okay, you have heard about it, right? So, so we need this process now. So we have to copy this and or you just type this one into your script. That's what you have to do. Well, this is not that bad. Again, if the equations of motion is very long, longer than 5 pages, then you have to type it. Or you have to have some better ways of copying this one and pasting this into your script. Okay. And I'll show you how I did this one. Okay. But anyway, is there any questions before I move on to the next example? I mean, next example means next condition. This is no slipping, no friction condition, but I'll think about frictions. I'll include the frictions next time. No questions? Okay. Then I'll move on to open friction case. Okay. So here now I added the condition that the coin is sliding, but there exists some friction. Okay. So this is more realistic, right? So before the coin was rolling on the ice, but then now this is rolling on some surface with the friction here. So now you have to include forces in here and here. Okay, does that make sense? Okay, so everything else is the same. The only problem is then how do we specify the forces here and here? That's what we need to do. So I'll just explain that part. So everything else is the same. So here, now this part is new part. Maybe it's a little bit confusing, but remember this. So we're here now. If you look at this one first, so we add. So tau 1 was already existed before, so it's fine. But then now we're adding f1, fx and fy. Okay. So that's a new part. So let's look at our diagram first. So your fx is in the x direction. So your fx is in this direction. That's the first component, and fy is in that direction. So we're adding that part, and that is added to your system. That's it, right? That's very simple. And so we simply added fx and fy to, so fx is for x4, q4, and fy is for q5, and so I think it's intuitive and it makes sense. Okay, so we added that part, and if you run it, then you still get the same equations. The only difference is now in your fourth Lagrangian equation and fifth Lagrangian equation, you're adding minus fx and minus fy. That's it. It's very straightforward. You're just adding fx and fy in the fourth and fifth equations on the right-hand side. Okay. Simple. And we do the same thing for getting the double dots, yes.
Can you explain that Jacobian part that you mentioned above?
Yeah, so I'll do that. Okay. Yeah, I'll do that soon. So now once you have all the equations here, expressions, then now you can get the inverse somehow, so that now you can get q1 double dot, q2 double dot, q3 double dot, and q4 double dot, and q5 double dot. So again, the reason why we need double dots is because of this part, right? So we need to do the numerical integration, and so we need this expression. Okay. All right, so And here I added the Jacobian part, and so for this example, I don't need the Jacobian at this moment. I'll mention this one in the next file, which is the rolling condition. Okay. So let me just move on. So again, so here we have fx and fy, and but we don't know what fx and fy is. We're just assuming some arbitrary forces. Okay, and we didn't specify whether this coin is rolling or not. Right? So this f can be fx and fy can be any forces. But now we are making the problem more specific. So let's consider the rolling condition here. So the rolling without slipping, okay, which is our interest, okay. So again, the kinematics is the same. So it's just the same, and then now Euler-Lagrange equation, we added the inertia, and then we defined the normal direction, the vertical direction. And then now we have to think about the rolling condition. So what is the rolling condition? So when we say rolling, what's happening? The velocity of ground is always zero, right? So here at the contact point P, your velocity of ground is always zero. But we have to be more specific. What is rolling condition? It's similar to that one, but I need some more elaboration.
Velocity of point Q, where it's at, coinciding with point P.
Yeah, that one has to be zero. That's important. That's important. You have to differentiate that because again, at the contact, your point P is always at the ground, on the ground, and so this velocity is always zero. When we say rolling, there shouldn't be relative velocity between point Q and point P and point Q. That's the condition, right? So the velocity of point Q when Q3 equals 0, it has to be 0. That is the condition, okay? So have that in mind, and let's look at our expression for velocity here of point Q. So now our task is to get the velocity component of Q. So to do that, we will look at the velocity of point C, which is the center of mass of the disk. That's already defined from our previous calculation, and that is saved in this center of mass velocity. Okay, and then we can also get the angular velocity of the reference frame C. So we have velocity, the VC and omega C. Okay, any questions? That's straightforward, right? So these are already given. Velocity and omega C is given. Now our question is calculate the velocity of Q given this. Okay, and you can just use those formula. If you know the velocity of one point, then velocity of the other point on the same rigid body, you just add the cross product of the angular velocity and the depletion vector. Can you do that? Right? We have done this one before, right? So then we have the expression, velocity expression, VQ. Well, velocity this is just a coordinate expression. So x, y, z coordinate of velocity q. I just converted this one into this expression. That's nothing, right? And it's expressed in terms of n1, n2, and n3. And if you look at that, so this is the final one. So the velocity of point Q in n1 direction or x direction is this. Okay, and velocity of Q in y direction is this. and the velocity of point Q in z direction is 0 automatically, right? Makes sense. So there's no vertical direction. Then what are those conditions? These two. So these two has to be 0, right? So that is the condition we need to add to the system. Okay. So now we're adding constraints to the system. Does that make sense? So it's a constrained or Euler-Lagrange equation, like dynamics. And we covered constraint part before, right? So we're adding, so therefore we have two non-holonomic constraints. The first one is this, which is the first velocity, the x velocity, and the second is the y velocity, and these two become 0. All right, so in summary, we have 5 Euler-Lagrange equations and 2 velocity constraints. So we have 7 equations, and then we also have 7 unknowns. For example, 5 is the double dots, q double dots, and then the 2 is coming from the constraint itself. So that means we need to have constraining forces. That constraining force is called the lambda, right? So we will have 7 unknowns and 7 equations. Okay. So since we have the constraints, let's add them to the system. So to do it, we're gonna use define constraints function. So we have two constraints. This is the velocity in x direction. This is velocity for y direction. Okay, and that has to be 0. What about the non-conservative forces in this case? It's just simply tau. What about the constraining force in x direction and constraining force in y direction? Why don't they show up in here? Conservative. Similar. It's actually well, the force itself. Usually, the force is not conservative in this way, but there are constraining. So it's actually it doesn't involve any movement. Right? It doesn't involve any movement. Does that make sense? So it's not contributing to the work. So we're not adding them in here, but we're actually adding adding them as a constraining force. Okay. Well, you have to be careful actually. So remember, if you look at our constraints dynamics, yeah, here. So Lagrange equation with the constraints, and so this is non-conservative forces, and then now you're adding the constraining forces here, right? So this part will be additionally entered in your equation, right? So so that's why we're actually separating this constraining force from the non-conservative force. Okay. So that's why I'm not putting that constraining force in here and here, but it's separated with the constraints. Okay. Does that make sense? Okay. So if we just move on, and we need to solve the constraint Lagrange equation, so it's different. So if you run it, and now we get the equations in this way. Okay. So we have 5 Lagrange's equation, and we have 2 more constraints, right? So total we'll have 7. Um, okay. So let's look at our constraint inverse first, okay, before mentioning uh, Jacobian. Okay, so if you just run the inverse, but then since this is constrained, so I added constraint inverse. So you get Q1 double that, Q2 double that here, Q3 double that, Q4 double that, Q5 double that, and then we have 2 more variables here, lambda 1 and lambda 2. So we found the expressions for that. So once we have double dots, 5 double dots, then we're actually good to go. We just need that information, and just type that in your script file, and then we're good to go. All right. Then what about those lambdas, lambda 1 and lambda 2? Okay, it's related to the constraining force. So if you look at our expression in here, so you just get the lambda expression. Then A transpose lambda is your actual your force, your generalized force. Okay. But then one more thing that I want to mention is this. All the forces on the right hand side in here, it is actually the same as Jacobian transpose times here force. That's the reason why I'm saying Jacobian is this. So if I go to the expression here, okay. So all the forces is actually expressed in terms of Jacobian transpose times some force. That's because remember that when we are dealing with the generalized coordinates, it doesn't have to be x, y, z direction. Okay. The generalized coordinates can be position vectors, or it can be your angular displacement, right? It can be anything that describes the movement of the system. We are choosing generalized coordinates because it's convenient to express the movement. It doesn't have to be this XYZ translation. It can be rotation as well, right? So that means we have to have some conversion between the different type of movement. If it's rotation, then now it will be a little bit different from the translation. Right? So that one will be covered by the Jacobian matrix. So we need some conversion of the coordinates so that we can relate this one directly to our working space. So that's why we need this conversion. So then this C is the actual constraining force, your XYZ force. Here, lambda is, even though I said this is constraining force, but this is generalized constraining force. In other words, it's just transformed forces. We have to convert this constraining force into the physical forces in XYZ direction. So that's why we need to do this Jacobian transpose multiplication. Okay, so that's a little bit confusing part. So yeah, we need to add this part. Okay, so basically think about this one as putting all the rotation translation into one plane, into one framework. That's what we're doing. Okay. So we have lambda 1 and lambda 2. So in Toolbox, we can actually use or get Jacobian, then it will actually calculate the Jacobian for you. Then what we need to do is you just simply multiply Jacobian transpose, as I said before here, Jacobian transpose times the actual force. It has to be the same as this this one. So if you just multiply Jacobian transpose and some of the your force x in x direction and force in y direction, then you'll get this expression. But let me just move on to the script because that's more important, I guess. So let's look at our Python script. All right, so let me just introduce what I have done, explain what I have done. So so again, if you remember our so we have x dot equals fx. So here so we need to have this expression. So we need to define x dot, or in other words f. So that one is defined in here. That one is defined in this f function. Okay. And then remember we had 10 state variables. Okay, in other words here, so we have from Q1 to Q5 and Q1 dot to Q5 dot, so we have 10 state variables. So that's why we have x d1 so 0 to 9, so it's not 10 variables. Okay, and here dx 0, dx1, dx2, dx3, dx4, dx5, 6, 7, 8, 9, it is corresponding to x1 dot, x2 dot, x3 dot, x4 dot, x5 dot, and dx9 is x10 dot. Okay, Python is using a 0 index, so that's why you're starting with 0. Okay, so don't be confused. And so what is x1 dot in this case? X1 dot is the fifth one, which is, so remember, so this one is x1, x2, x3, x4, x5, and this is x6. So your x6 is the velocity. So that's why your x6 dot, no, so your x1 dot is actually x6. Does that make sense? And x2 dot is x7. x3 dot is x8, things like that. So these are okay. These are how the state variables are defined. The last 5 dots are the dynamics. Okay, so that dynamics actually is Q1 double dot, Q2 double dot, and things like that. So basically this one is Q1 double dot, Q2 double dot, Q3 double dot, Q4 double dot, and Q5 double dot. And to get that, you have to have that expression, and that one is just a second. Let me just open them in here. So I defined it in here. So I added another Python script. So now here, so this is the Q1 double dot expression, and so this is the Q2 double dot expression. So this is the Q3 double dot expression. Okay. This is the Q4 double dot expression, And finally, this is Q5 expression. Okay, and how do I do it? It's just copying copying this one. Do you trust me? And hope so. And so, for example, if you just look at Q1 double dot, this is the same as this. Well, where is the sec? Sec is 1 over cosine, and Python does not allow uh, secant. That's why I use 1 over cosine instead of secant. But other than that, it's the same expression as in here. Okay, you just copy this and just put them in here. Does that make sense? And there are some other convenient way. So I mean, copying the equations is quite pain in the neck, but then we can somehow use Mathematica function to convert our expression for our convenient. Here, I'm gonna post this script file for you. But if you look at here, so this is how I use the function for converting our expression for Python script. So this is actually what we get finally. Okay, because the expression you get here, this cannot be used in Python script directly. You cannot just copy and paste this one. But if you use some type of conversion, for example, your Q1 of t, we just want that to be Q1. Okay, your Q1 dot t, we just want it to be Q1d for our script. Does it make sense? Then we can just simply convert them into this plugin expression. Okay, and then another one is if you look at the Mathematica, we are using a big C, capital C, and capital S. So we just convert that one into sine and cosine because Python use this small s and small c, or small t and small s for functions. So you just use that conversion. And finally, Fortran form is a embedded function in Mathematica. What it does is it is actually converting all the brackets into the parentheses. Okay. So Fortran is another programming language. So and Python is actually using very similar syntax. So that's why we can use this one. Then it will convert everything into Python-friendly expression this way. Then you just simply copy this one into your script. So, for example, I just copied this one. You don't need to copy the list one, but here, let me just copy everything. And so what you're gonna do is enter this and remove list and remove the last one. And then, so this one is not the minus sign, but this is the line separator, so you can just remove this one. And then add this one to the end of the previous line, like this. Okay, so that's it. That's all we need. So in this way, you don't have to type everything here. And that is actually the same as Q5 double dot, as you can see. So you can clearly see that they are exactly the same. So that's how we can add very complicated expressions. Yes.
What about the secant? Is there any copy paste of that?
Yeah. So secant. So if you have the secant expression, for example, if you have secant Q2, then you just make it 1 over cosine. No, don't do it. I tried it and it wasn't reliable. So you just simply manually do it. Okay. So once we have that expression, let me just spend 2 more minutes. Okay. So we are now done with the dynamics expression. So we just defined our f function. Then now we have to run the numerical simulation, which is done by the IVP, initial value problem. That is actually a package from SciPy. Okay, you may heard about SciPy before. NumPy and SciPy are the most two commonly used packages. And we can use the SciPy package to do the integration, and we can use the initial value problem. So that means if you are given initial condition, then this SciPy function will do the numerical integration for you guys using many different algorithms, but here we're using RK45, which is Ranjikuda's fourth order, fifth order one. So it will automatically change its time step so that it will give you the best result of the simulation. Okay, and once you have that, then now you can just plot them. This is simply the plot function. And then this part is added. This part is how I perform the numerical the animation. Okay, so you don't actually need this part. This part is only for the visualization purpose. You can see the problem easily. But if you don't have this one, then what you can do is you can simply run Python this script file and run it. Then you'll get this one. This is what you need, right? So then you can just interpret how Q1, Q2, and Q5 or whatever variable you want to investigate, and you can explain what's happening. Okay. But if you want to do something more intuitive, then now you can just run this simulate animation part. I'm not gonna explain this animation function for you guys, but I'm gonna post this one into the in-campus so you just study that script. But if I do it, and now as you can see, this is what's happening, right? So that's it. And then now let's do some parameter studies. So that means now if I just decrease the spinning speed, so I added 100, so that means it spins very fast. If I just move it, so it's 10 times slower, then what happens? And I introduced 0.01 radian tilt angle, so that means tilt it a little bit toward to the left, right? So then let's see what happens. If we run it, then as you can see, now this is the behavior, and the green one is Q1. Q1 is your tilting angle, not tilting angle, your steering angle. So it changes direction very drastically, and see what happens. So this is what happened. So it's actually changing its direction. If you look at it from the above, it's not moving a lot much, but actually it's changing its direction much. So that's why you see a lot of changes in Q1, but actually it's remaining always almost in place. Does that make sense? Okay. And finally, one more thing. Sorry about the delay, but I think it's important. Here, what about our tau? So tau was our force, right? So I set it to be 0. But if I introduce some non-zero forces, then see what happens. Okay, I think that's important. If you have tilt angle, and if you introduce some torque, what do you expect? If it's something like you're riding a bicycle, if you are tilted toward the side, and if you're just pedaling more, you're actually regaining your balance. And that's actually happening in here. So to do that, I'm gonna just go back to our original fast rolling condition and run it again. There's some interesting phenomena happening. Well, that is actually there is some numerical issue here. SciPy is not that perfect in handling this thing. So this is actually artifact. This is not the true result. Okay. And if I just zoom in here, you will see a lot of noise. I mean here. So do you see that this is very undesirable result, and that's because this numerical simulation is unstable. And the reason why it has instability is because of this abrupt changes in your force. Okay, so to avoid that abrupt changes, I can just introduce some smoothing function. Okay, sorry about the delay. So if I just adding this smoothing function, then the numerical result will be better. So I think this will be the last one. So now we see some better result, but then it's still not that satisfactory. But the interesting thing is this one. So if you look at Q2 was our tilt angle, right? We started from 0.01, but then you see that it converges to 0, and it stays there. Even though we have oscillation, that's because of the numerical instability of the method that we're using. Okay. All right. So by introducing the torque, we are actually stabilizing Q2. And yeah, that's all I have. Right.